Natalie Nelson. I'm an assistant professor in the Biological and Agricultural Engineering Department and a faculty fellow at the Center for Geospatial Analytics. And it's my pleasure to be able to introduce Casey Dietrich today, who's an assistant professor in the Civil, Construction, and Environmental Engineering Department. He runs the Coastal and Computational Hydraulics team, and his group is really focused on improving predictive models for coastal hazards. In particular, he's worked quite a bit with storm surge modeling and analyzing and predicting impacts associated with hurricanes. So he was even recently featured on NPR, The State of Things, for his work related to Hurricane Florence. And so please join me in welcoming Dr. Dietrich.
So thank you, Dr. Nelson. Thanks to the center staff for inviting me. Thanks, everyone, for coming. The invitation for this seminar said something about frontiers in geospatial analysis. I don't know that we're going to get to that lofty level today, but I just wanted to share some of our research and hopefully get connected a little bit better with you guys as we go forward. So as Dr. Nelson said, my research is mostly on predictive modeling of coastal hazards, a focus on storm surge and coastal flooding. The work I'm going to present today was done by one of my master's students, Nelson Tull, over the last couple of years. And our focus here is really real-time forecasting. So we run our models as a storm is coming, make predictions about what areas are going to get flooded, and then share that guidance with stakeholders. And so this work was with North Carolina Emergency Management, the state-level emergency managers, pretty closely with Tom Langen and the North Carolina Flood Mapping Program. And then also we're part of a larger team of storm surge modelers in the state, including Brian Blanton, Jason Fleming, and Rick Ludick. So to give away the ending, this is an example of our model. This is Hurricane Florence from 3 weeks ago. The vectors are the wind speeds, the wind velocities, and then the colored contours are the water levels along the coast of North Carolina. And we'll let it loop a couple of times, but you'll see the storm comes in, slows down as it's approaching Wrightsville Beach and Wilmington. A lot of water building up in the sound and up the river estuaries. And then as the storm makes landfall, a lot of storm surge along from Wrightsville Beach up to Topsail, and it interacts with the tides and comes up and down a little bit as the storm moves through. So this is our model. We're trying to represent the entire state coastline with what we think are high levels of resolution, representing not just how the coastal ocean will respond during the storm, but also how it will interact with the coastline, the Barrier Islands, in the sounds, and up through the river estuaries, and bringing water over land to critical infrastructure. Today I have kind of three parts to the talk. I want to talk about Florence and what we did and what we've learned so far, and then get into the research project of this master's student, Nelson Tull, and kind of talk through how we're trying to improve our flooding guidance as we go forward. So the first step in our model is to represent the coastal ocean, and for that we use an unstructured mesh. This is the mesh that we use for North Carolina. It actually extends out into the Atlantic Ocean and Caribbean and Gulf of Mexico. And we call it unstructured because we're using triangular finite elements of varying sizes. And so they can be really large out in the Atlantic Ocean. You might have triangles with edges with lengths of tens of kilometers, 100 kilometers. And then we can shrink them down as we get closer to shore and critical infrastructure. So if we zoom in first to the South Atlantic Bight, a little closer to North Carolina, you see we're starting to increase the resolution to a few kilometers on the continental shelf, 500 meters or so closer to the coastline. And then if we zoom in, the top one is showing a zoom kind of close to where Florence made landfall. And so really shrinking down the elements to a few hundred meters, tens of meters, sometimes in some of the small scale coastal channels. And even zooming further toward the Neuse River estuary at the bottom there, really packing in these elements and trying to represent what's going on. The more triangular elements, the more fine elements we have in a region, the more accurate our simulation results should be. And so we're putting them in places where we think the water levels are going to be important or where they might be changing rapidly. So along the Barrier Islands, along the inlets, up in the river estuaries and some of the small-scale channels, and trying to pack them in as much as we can. Our models, we use a coupled modeling system, and this is kind of my claim to fame. This was my PhD work. I coupled ADCIRC, which is a model for long waves like tides and storm surge, with a model called SWAN, which is for short waves, the kinds of waves that you would see if you were standing at the beach, the waves with periods of 10 seconds or something, the waves that are generated by the wind. These models run at the same time, and they pass information back and forth to each other through local memory. And out of the models we get output, we get predictions of water levels along the coast, currents, significant wave heights, peak periods, everything like that. Some inputs that come in, the big one is the unstructured mesh that I just showed, but also we need drivers for the coastal ocean behavior. So we need to understand what are the tides going to be over the next 5 days or however long the simulation is going to be, what winds are going to forecast, are going to drive our model, and then we can bring in river flows at some of the upland river flux boundaries. We can do this in real time. We have a scripting system that's run during storms, and if everything's working correctly, it should all happen automatically. So you push one button, you start up the scripting system, and it should just run, produce forecasts every now and then during the storm. Hopefully you don't have to worry too much about it. Of course, that's not what really happens, but that's the goal. We run this system all the time, so it's running today. In normal conditions, we use atmospheric forcing from a model from NOAA INSEP that we convert into a format and we use to drive our models. During the storms, we're using the forecast advisories from the National Hurricane Center to drive our models. So every 6 hours, the National Hurricane Center puts out a new advisory and says, this is what the storm track is going to be, this is how large the storm is going to be, this is the maximum wind speed. We bring all that information in, and then we use that to drive a prediction of the coastal ocean behavior. So that happens every 6 hours. It takes maybe an hour to run our models in an HPC environment, and then we're giving the guidance to our stakeholders. There is a public website, and hopefully you've seen that, the Coastal Emergencies Risk Assessment site, SARA, where we post our results, but also we send them directly to people like the state level emergency managers, local offices of the National Weather Service, anyone who needs this information to kind of support their decision making. So during the storm, this is an example of what we were putting out. This is a forecast from Florence. If you remember, Florence made landfall early on Friday morning, September 14th. This is a forecast, and it says in the upper left there, from September 11th. So 3 days before, Tuesday at 5 a.m. Eastern time. And I'm showing two things. On the right side is the contours of the maximum water levels during this forecast. So starting at Tuesday at 5 a.m. and going forward for 5 days, this is what we project will be the maximum water levels. So at this time on that Tuesday morning, the track was trending a little farther northward than what actually happened. Has a landfall close to Topsail Beach, and large impacts to the east of the track along the coast, and then also large water levels up the estuaries and into the sounds. The contour levels here, the darkest red is 3.5 meters, so 10, 11, 12 feet of storm surge. And on the right is water levels at Beaufort. So Beaufort is somewhere here close to Cape Lookout. And the blue line is the observed tidal signal at that location. The red vertical line is where we're starting our forecast, and then the yellow is our predicted water levels at that location. So a peak here, if the storm had followed this track with these other storm parameters, the peak water levels at Beaufort may have been 7.5 feet, something like that. So we're going to step through every 2 hours, or 2 advisories, so every 12 hours. So Tuesday at 5 p.m., the track was coming a little farther south now. The earlier Tuesday one, those were the tracks that had the storm coming right over Raleigh if it had followed on that same track. But now it's coming a little farther south and moving toward Wilmington, and we're seeing larger water levels spread out more along the coast, and the peak water levels in the estuaries aren't quite as bad in this prediction. 12 hours later, Wednesday morning, the track has shifted really far south, and now we're getting large water levels along Wrightsville Beach, down to Carolina Beach, and and really big impacts closer to Wilmington. And then the sound's not as important, not as high, and the peak water levels at Beaufort near Cape Lookout are a little lower, 5 feet or so. Another 12 hours, and here, these are the forecasts where now they started to understand that the storm was really going to slow down and take its time as it made landfall, and a slower storm translates to larger water levels, larger peak water levels along the coast, and so we're seeing a similar track here 12 hours later, but a slower storm, higher water levels are spread out a little bit further, and as we kind of come through, this is September 13th, so Thursday at 5 a.m., just about a day before landfall, and this is getting closer to what really happened with high water levels both along the coast and up in the sounds and the river estuaries. And just for comparison, this is the hindcast that we did after the storm, showing those higher water levels, but also now we've got the light blue, the observations of the water levels at Beaufort, and a really close match to our model predictions. So given the right track, the right other storm parameters, we can do a pretty good job of predicting what the water levels will be along the coast. So that's kind of what we did. That's the goal, is to be able to do these real-time forecasts. So what's the problem? It sounds like a good story so far, hopefully, that I know what I'm doing, or that our research team knows what we're doing and we're putting out a good product. So what's the problem? Well, if we really zoom in, you start to see some issues with what we're putting out. And so this is a zoom in the Neuse River estuary. The grayscale here is a 50-foot topography DEM that we got from the state level, the North Carolina Emergency Management, our partners there. And the yellow colors, the yellow-orange colors, are maximum water levels from Hurricane Matthew. So from now on through the talk, we're going back a couple of years to Hurricane Matthew. Yellow here, Matthew stayed offshore, so the water levels were a little lower in the Neuse River. Yellow here is 3 or 4 feet above sea level. But the problem is, so you can kind of ignore in the middle, we're kind of masking out areas where there isn't any DEM coverage, so we are predicting water levels in the middle of the Neuse River estuary. But the problem is at the edge. So you can see the edge of our water levels, our predictions from our model, doesn't even come to the coastline in the DEM. There's a white space in between, and if you use your imagination, you can almost see the triangles in our mesh. Like here is an edge of a triangle, and we're not resolving that coastline with enough resolution. The triangle edges in this part of our mesh might be a couple hundred meters on a side, and that's high resolution for our model, but it's low resolution for this part of the world, and especially it's low resolution for our partners at North Carolina Emergency Management. They want to know not just how high the water level is going to be in the middle of the estuary, but how far overland the water levels are going to come, which buildings are going to be flooded, what are the impacts going to be. So we need to bring our predictions to the infrastructure for them to be helpful. So that's where we get into a geospatial problem to solve, and that was the focus of Nelson's master's research the last couple of years. This is the point in the presentation where I have to make a confession. There are a lot of geospatial wizards in this room. I am not one of you. So what we're going to do here is conceptually pretty easy. We want to take our water levels, just extend them outward to where they intersect with the ground level. That may not be impressive to you if you're a geospatial wizard, but it was a lot of work for us, and I think a nice opening into some of the techniques that we can continue to use going forward to improve what we're doing. So we want to enhance the flooding guidance that we provide to the North Carolina Emergency Management. Right now we're providing water levels at our mesh resolution. So we have about 600,000 vertices, the vertices of those triangular elements in our mesh, and a minimum spacing of maybe 50 meters in certain locations along the coast. Normally it's more generally it's maybe 200 meters, something like that. North Carolina Emergency Management wants to combine our water levels with other data sets. They have a data set with the footprint of every building along the coast, for example, so they could do an intersection and see, which buildings are we predicting to be flooded. In that case, what we want to do is put our water levels onto a structured raster with equal spacing and then ease that those kind of combinations. The 50-foot raster, which is not that fine, still has 400 million raster cells covering the coast of North Carolina. So 3 or 4 orders of magnitude more points than what we're starting with our unstructured mesh. So need to do two things: downscale, so increase the resolution in our water levels coming out of our model, and then extrapolate them horizontally until they intersect with the ground surface. And here's the $50,000 figure. And I say $50,000 because this was figure one in a proposal that was funded for $50,000. But this is conceptually what we're trying to do here. The mean sea level might normally be down pretty low, but during the storm the water levels are going to come up, and these large blue shaded regions, this might be the resolution in our model. Maybe this is about 200 meter elements in that Neuse River estuary. And we can resolve part of the coastline and bring water to where it wasn't normally, and might maybe show some buildings already being flooded in our forecasts. But really, this water should be projected a little farther inland, over roadways where appropriate, or intersecting with other and flooding other buildings to be a little more accurate. So downscaling and extrapolation here. So goal: enable data-driven decision making, and objectives: extrapolate. The other thing is this has to be fast, so we need to be able to do this every forecast cycle. We're already spending an hour running our high-resolution coastal ocean model in an HPC environment to get these forecasts. We can't add in a lot of extra time onto that process. We need to be getting these results out to the emergency managers as quickly as we can. So this needs to take no more than 10 to 20 minutes, and hopefully faster. So we used grass. This was very fortuitous. Nelson was in the GIS 582 with Professor Matasheva and Vashek, and was learning exactly the tool that he needed to be able to do this work. Grass is developed here partly with researchers here in the center, but also worldwide, and is known for being extremely fast for raster processing, so well suited for this work. Interpolate the general steps. We interpolated the ADCIRC water levels to 50-foot DEM raster, extrapolate them into the small-scale channels and floodplains, so expand the raster outward, and then the key step is to remove any cells that become flooded in that process that shouldn't. So if they're not hydraulically connected to the water levels at the coast, then we don't want to put water there. And the example of that might be if you have a barrier island with a dune, if the water level is stopped by that dune, then that's what we want. We don't want to put water behind the dune and show flooding where it shouldn't be. So that step to remove the isolated cells is important. And then convert back from raster to polygon for distribution. So a little toy problem here. Here's our little toy estuary. We have grayscale here. Maybe this is the DEM that we're working with, the raster DEM. And so lower elevations at the edges of the estuary, and then coming higher as we move away. This might be, in the toy problem, the water levels that we're getting from ADCIRC, so on a coarser resolution, and increasing from 2 to 3 to 4 feet above sea level as you move up into the estuary. We want to be able to take these water levels and then extrapolate them outward to where they intersect with the ground surface. So that first step, the interpolation step, is costly, at least the way we're doing it right now. We need to take the 600,000 vertices for our North Carolina model and put them onto 400 million raster cells. Even for Carteret County, which is kind of where we started, just pick one county and do an analysis, there's 28 million cells, so still several orders of magnitude larger than what we are working with out of our model. We did as much as we could. We pre-computed some inverse distance weighting, and we have an input file with all those weights pre-computed. It still takes 5 minutes to do this work. The very last thing that Nelson did before he left, actually after he defended, he came to me one day and he was like, I found a way to do this in like 10 seconds. And I was like, well, I wish I could take back your master's degree, and we should make you do that. But no, he left it for the next student. So Carter Rucker is here. He's going to pick this up, and the first task that he has this fall is to take this 5 minutes and make it 10 seconds. And we'll see. I'm not a grass expert, so we'll see if Carter is learning in 582 what he needs to know. So then we import this new raster into grass, and we're making significant use of this module r.grow, which is already written and designed exactly for this task. With r.grow, you take a raster and you can expand it outward using the values in the raster and comparing them against other data sets. So we had to make a few changes that are specific for our problem. We wanted to compare just to the ground levels in the DEM, and if the water level is higher than the ground level, then keep it. If not, throw it away. And so we have an r.grow.modified that Nelson wrote that does this. So expand only into null cells if the ADCIRC value is greater than the DEM. And we have to pick a radius there to expand, and so that was some give and take, trying to understand how far we can expand and still be accurate and still be physically realistic, and then enforce hydraulic connectivity. And then convert back to polygons, and so we're binning at half-foot intervals as we build these polygons, and then sending a shapefile by email to North Carolina Emergency Management with the guidance ready to go in the format that they want. So as an example, here's Carteret County. This one, we picked this as a test case to start out with because it has a little bit of everything. There's some barrier islands, there's some inner waterways, some estuaries. It connects to the inner sound, a few islands in there. So this should be a nice test case of what we're doing. And what I'm going to do is first zoom in to just a little section of the barrier island down near Cape Lookout. And so this is what the DEM looks like there. In the grayscale, the highest points, at least in the contour range, go up to about 25 feet. And those correspond to the dune, the coastal dune along the front of the barrier island. In front of the dune, and especially behind the dune, the ground levels are a little bit smaller. And then you can see the connectivity back to the sound on the back side. Put our ADCIRC simulation on here. So this is one of the forecasts from Matthew. And what's happening here is the winds are blowing from the north. And so we have elevated water levels on the north side of the barrier island up to 6 or 7 feet. And on the south side of the barrier island, the winds are blowing water away from the island. And so lower water levels, 4 feet or so. And this, again, this discrepancy between our coastline and our model and the actual coastline in the DEM. In the southern part of this picture, we've actually got overwash, the overtopping of the dune. So the elevated water levels on the backside are coming over the dune and connecting to the ocean side. But in our model, at least, the dune crest is too high in the north part of this picture, and that's preventing flow coming from the north to the south. Run our script, so extrapolate those water levels outward, and we get something like this, where there still is a part of the dune that has a ground elevation higher than 7 feet, and so we're not showing water there. But on the front side and the back side, now we've got water closer to where it's supposed to be. And if there are any residences here, or if this was a region that was populated, we would be putting water predictions of flooding into those communities, and maybe a little more useful for the emergency managers. A section here where you actually get a connection from 7-foot raster cells to 4-foot raster cells. And it looks kind of jarring to have those right next to each other, but physically that kind of makes sense. You would have the higher water levels coming to the top of that dune, overtopping and kind of spilling down to the lower water levels on the other side. For the whole Carteret County, it starts to look something like this. So this is a zoom in on an estuary near the coast. Before, we've got water levels up into the estuary, but maybe not always to the coastline, certainly not into these smaller sub-estuaries off the main branch. But when we run this script, everything kind of gets expanded outward, and we see a nice representation of what the flooding, what we were kind of predicting the flooding to be. And for the islands here, we can see a before and after. And the neat thing here is you start to see some of the striping where the water levels are kind of filling in these low regions in these agricultural fields. And so that's being picked up also in these predictions. Water coming around this bend here and filling in the way it's supposed to in this feature that's a little lower resolution than what we can represent in our models. So to check this, does this work? We can actually do the intersection and connect the flooding guidance with the known building footprints provided by NC Emergency Management. And so for a hindcast of Hurricane Matthew, just in Carteret County, our forecast water levels were showing flooding in about 2,400 buildings. After the enhancement, that increased to 3,800. So a 60% increase in the flooded buildings that we're predicting. And that's important. North Carolina Emergency Management is looking at this during the storm to try to make decisions about evacuation or where to deploy resources so that they're available after the storm. They also are computing predicted storm damage estimates. So if we have water or waves at these buildings, they can convert that into a dollar amount of damage at those structures. And that helps them plan for their assistance requests to FEMA or to other agencies. So being able to do that in real time during the event helps them get money faster after the storm to help rebuild. So for the entire North Carolina coast, we had to speed up the process. So it was taking 30 to 40 minutes just to run this interpolation, extrapolation script for the entire North Carolina coast. So we did a really basic parallelization. We took this 400 million raster cell representation of the North Carolina coast and cut it into horizontal strips that overlap by 500 cells each, and then sent each of those strips to a different CPU. So we can run on 16 CPUs. That sped it up. It didn't scale linearly, so we're still taking 12 to 15 minutes every time, but that's good enough for now. The North Carolina Emergency Management, our partners there, are happy with that kind of time frame. They're willing to wait another 15 minutes to get these post-processed water levels. And if we look at the entire coast, this is a before and after in the Albemarle Sound for another Matthew hindcast. And you can see all the additional complexity that we're putting water levels up these small-scale channels, putting them up to the coastline. Matthew was a good test case to start with, but it will be really interesting to see during Florence the benefits of the before and after if we go back and really do a nice comparison. More work for Carter to do the next little while. And so we've been doing this the last two hurricane seasons. Harvey and Irma last year didn't really come to North Carolina, but we were still running predictions and sharing them with our partners. And then this year during Florence, we ran a forecast starting Sunday and going all the way through the storm, 4 a day. And so every 6 hours we were sending these guidance products to our North Carolina Emergency Management. Also for Michael, Michael still had some coastal impacts, a few elevated water levels on the sound side of Hatteras Island and in other locations. So we were sharing results there too. And right now we're running it here at NC State, but what we really want to do is get it over to Renzi in Chapel Hill and integrate it into the automated system. So the last little part here is trying to get a little bit more at how well this is working. And our hypothesis is, the other way to do this, instead of using graphs and doing the extrapolation, is what if we just increase the resolution in our coastal ocean model? And instead of having elements of 200 meters on a side, what if we had elements that were 50 feet on a side, the same resolution as the raster DEM? And so Nelson did this. He took, just for Dare County, North Carolina, he took the DEM, and for every DEM cell, he put down a point in our ADCIRC mesh. So it's, at least in Dare County, it's no longer an unstructured mesh. It is structured. It corresponds exactly one-to-one with the 50-foot DEM. And just for Dare County, just doing that increased the overall size of our mesh to 5.7 million vertices. So a factor of 10 in size, and thus a factor of 10 in computational time. Instead of an hour to run it would take 10 hours to run this mesh. But at least this allows for a one-to-one comparison, at least in the accuracy. Are we getting roughly the same results with this extrapolation method that we would if we were putting the effort into resolving this in our model? The model should incorporate a little more physics. We're not just extending the water levels horizontally. We're accounting for the wind direction and the local bottom friction and a lot of other driving terms in those equations. So a comparison here for Dare County. So 3 pictures here. The base is before we do anything. So this is the North Carolina forecast water levels that we would be doing just in real time every day. The enhanced is in the middle here is the results from the extrapolation. So this is coming out of grass and putting the water levels farther over the coast. And then the refined is on Nelson's 5.7 million point ADCIRC mesh. And on later slides I'm going to zoom in both on inland Dare, which is this large body of land here. And then also we're going to zoom in on a section of Hatteras Island, so down here. But you can start to see some differences already. We've got some flooding already here in the base model on the kind of east side or west side of inland Dare. And so that gets extrapolated a little further in the enhanced version. And in the refined, where we're not doing the extrapolation, we're just running on the high resolution ADCIRC model, we're seeing a bit of a different flooding extent here. So we can compare for the whole Dare County. The base run puts water on 185 square kilometers of land, so about 18.6% of the total land area of Dare County. When we run the enhancement, we increase that by about 10.5, 11%, so 29% of the land area becomes flooded. And in our refined model, it's actually lower. It's 13%. So we're way off here. We should be showing less flooding than we're getting, but if anything, we're making things worse with the refinement. What's going on here? And the problem is inland Dare. So you have this huge body of land here, and it's all very low lying. This is mostly marshland connecting to Roanoke Island and Manteo and going out to Nags Head. And we're already over predicting the flooding extents in the base model. So putting too much water on the west side here, too much maybe on the north side. And as we do the enhancement, that just gets worse. We push that a little further out to where the water levels intersect with the ground surface. But if we were running on a higher resolution mesh, we could represent the friction of the marsh a little bit better, some of the small scale hydraulic controls, and we wouldn't be putting the water levels as far overland as we maybe should be. If we go to the Barrier Island section, the results are a little bit better here. So here, starting out in the base, only 2% of the water of the land area is flooded. And with the enhancement, we're up to 14, and that's a little bit closer to what we think really should happen here, where during Matthew, at least this hindcast of Matthew, it should be closer to 11.5 or 12%. And you can see that here. The coarse ADCIRC mesh doesn't really represent the water levels building up on the sound side of Hatteras Island, but as we do the extrapolation, we push them a little closer to the dune, and we're getting a better match to what might actually be happening. So in regions where the ground surface is really flat, like a coastal marsh in inland Dare, this may not be a good method. We may not be adding any value here or increasing our accuracy. But in other regions where the ground surface has a higher slope, where the topography is coming up pretty quickly, this might be a good method. We might be adding value and increasing the accuracy beyond what we can represent in our models. So we've communicated this guidance to our stakeholders, and I hope that they're using this as they're kind of working through their decision making. There's parts of this that are better than others. And so that's where I'm hoping continue the conversations with people here in the center. There must be smarter ways to do this where we're not just extending horizontally without any real physics, but can we also look at what is the local roughness in the marsh, which direction is the wind blowing, can we be smarter about how we're extending the surface. Because we really need a step like this. We can't just increase our resolution to 50 foot everywhere. That model would be way too complicated to run in real time. And so we need some combination of physics-based coastal ocean model and some sort of, hopefully, physics-based geospatial technique. So that's all I have. Thank you for your attention today. And thank you to Vashek and Professor Matasheva and everyone here in the center for leading us down this path. Thank you. I think we have time for questions. Yeah?
So you talked about how the models changed how many predicted buildings you were going to flood. Were y'all able to compare that to the actual data?
We would love to. It's tough. The flooded building data sets are owned by FEMA, and there's all kinds of privacy issues attached to them. I know a colleague at UNC Chapel Hill who just got access to one of those data sets for Hurricane Isabel 15 years ago from 2003. And he's been fighting for most of that time to get all the privacy issues squared away and to get FEMA to release that data set to him. So we haven't really started down that path. I think the flooded area is going to have to be a proxy for flooded buildings for us. If we can get the flooded areas to be correct, then hopefully the number of flooding buildings will be correct too. Yeah, I'd love to see that data, but I think it might be too difficult for us to get our hands on. Yeah, I mean, maybe I'm wrong. Maybe somebody in the room knows better than I do. Yeah.
What is the basic principle of the decision making?
How do you mean?
When you do the forecasting, the main principle.
I mean, our goal on our side is to predict the coastal flooding extents. So what areas are going to be flooded and for how long during the storm. And so that's where we're kind of building these coastal ocean models. I can speak a little bit about what the emergency managers are using that data for. It's partly during the storm to make decisions about evacuation and resource deployment. So what areas need to be completely evacuated, what other areas we can leave there, but we need to bring water or be ready to get the power back on, those sorts of things. We're just one data point that they're looking at. The National Hurricane Center is also putting out predictions for flooding and storm surge, and there are also other models for other parts of the problem that they're looking at too. And then, like I said, the other decision-making thing that the decision they're trying to make is about the damage estimates, so that those are ready as soon as possible after the storm, so that they can go up to FEMA or to other agencies and request relief, so aid to help people rebuild or help get the power back on or help to rehabilitate everybody. Does that answer your question? Maybe not. Okay. Yeah.
Thank you for the talk. That's been very interesting. Since you say you're providing a GIS shapefile to the decision makers as the output, the final thing you're giving, and that's just a snapshot in time, what is the temporal distance between when you create it after it takes the 15 minutes? How far out are they looking for that snapshot in time?
As soon as we can give it to them. So is that what you're asking?
Yeah, sorry.
No.
Let me try it again. When you do the prediction and you produce that GIS shapefile and you send it to that organization, what is the time difference between that point and when you're actually trying to predict for?
Oh, so for example, Florence made landfall on Friday morning. We're making predictions the whole week ahead of time. So Monday, Tuesday, we're providing data sets to them that include what's going to happen over that next 5 days. It includes the landfall of the storm. Is this not your...
Multiple GIS shapefiles, each one representing a future point in time?
We are providing for each, so every 6 hours there's a new forecast from the National Hurricane Center with a consensus track and other storm parameters, the size of the storm, the radius to maximum winds, etc. So every 6 hours we do at least one simulation. We'd like to do 4 or 5, so the consensus track and then a few perturbations if
And
the
that
track
simulation would be what you expect to happen
in the next 5 days
for all.
for the entire rest of the storm. So every 6 hours, we're providing a shapefile to them that shows the maximum water levels over the next 5 days. And then 6 hours later, we're sending another
So
one.
it could be at any point over the next 5
Yes,
days.
yes.
It would be the maximum.
Yes, that's
Okay,
correct.
got it.
Yeah.
So, and then do you say what time that might happen?
We can. They haven't asked for that, actually. When I was a postdoc at Texas, we were running the same system for the Texas coast, and there the state level emergency managers really wanted that information. So not just what is the maximum water level, but when will it occur, how long will the water levels be above some threshold, and so we were passing multiple data points to the Texas State Operations Center. Here in North Carolina, I think we're still kind of educating them on what's available coming out of these models and what we can provide.
I would just think that would be absolutely essential to determining where you send crews at what points in time.
Yeah. The other, that is important. The other way that they can look at these predictions, and they do, is through the web-based service, so the Coastal Emergencies Risk Assessment. And this hydrograph is actually a screen capture from that site. So on that site, not only are we showing the maximum water levels, but you can also see time animations of the water levels spatially, and you can click at any point along the coast and see the hydrographs. So I know that they're looking at that. I just don't know which pieces of that they're looking at, and they haven't asked for that in any other specific format bit other than what's on the website.
That's
Okay.
exactly.
Okay. Other questions? Natalie?
So there's been a fair amount of discussion about how wetlands can be used to mitigate impacts related to storm surge. And I'm wondering, with this model system based on, in particular, the higher resolution product that you showed at the end, would it be possible to switch out areas where you have wetlands and then just as a simulation to test this principle, you could swap out the wetlands with, say, developed area to see if that impacts the distance of storm surge and how far it travels inland, or would this model not really be?
The physics-based, our coastal ocean model, we certainly could do that. And there have been a few studies in that direction already where we changed information about the local friction or some of the other ground cover characteristics, switch from marsh to something that's more built up, and then it does have effects on the storm surge and the flooding propagation. The geospatial technique is too dumb right now to be able to look at those things, but that's a direction we'd love to go in. Yeah. John?
When you're extrapolating, you're basically just saying if this land is below this water level.
Yeah.
Okay.
Yeah. And we're not looking at anything about ground cover or, yeah. Again, Carter has his work cut out for him. There's another question?
So you said you are using 16 cars, so it sounds like you are using one node, but you said you are using
Yes, yeah, yep.
So will you be, or like, why are you not using multiple nodes?
We tried that. The parallelization technique that we're using is we're just cutting that raster into horizontal strips, and they need to overlap. So because of the radius for the RDOC-RO technique, if the radius is 30 cells, then you need to have the horizontal strips overlapping by 30 cells so that each CPU, as it's doing its GRO process, it's doing it correctly. And so if you start cutting those into more strips, if you do it on 32 or 48 and everything's still overlapping, you start to get diminishing returns where you're increasing the workload faster than you're increasing the number of CPUs that are available. So we need a smarter way to parallelize that is more scalable. Yeah. I feel like it's all things that we're doing wrong here today. John.
The unstructured mesh, how do you decide when and where to decrease the size of
It's there are some rules of thumb or some automated ways of doing it, but it's mostly art. It's as much art as it is skill, and it's really based on the scabs and the bad experiences we've had over the last 10 or 15 years. We know that this won't work if we have the elements of this size or laid out like this, so let's try it a different way. And in terms of the sizes of the elements, it's really a give and take between, we'd love to have them as small as possible, but we just don't always have the CPU resources available. So really just trying to put them where we think they're going to be most valuable, where the infrastructure is or where the flow is changing most rapidly. That's kind of a wishy-washy answer to your question, but it's will continue to be an active research area, how to best optimize that layout. Yeah. Okay, thanks everybody.